because one can advance slides and show something on the screen.
How to update that slide before I send it to you?
Huh? Let's give a benefit of doubt to Java template.
Okay.
The okay, very good. Probably we can start. So David will need to fulfill requirements of the department, chemistry by chemistry, which means giving literature review seminar and it will be graded and friendly colleagues will give aggressive questions. So it's better to give hard time to David right now so that he will be prepared to complicated questions when it will be true time for the talk. And since it is not forbidden to match the research area and presentation. Sorry for that. That's okay. Thank you. He will be speaking about two-dimensional perovskites, teaching us what they are. Everyone is encouraged to make notes and submit them later to David for improvements. I have a backup of plans.
Thank you.
Yeah, please go ahead.
Okay. So, I'm David Graupner, and I'll be talking about two-dimensional organic, inorganic hybrid perovskites.
Now I heard for the first time how you pronounce your last name. So it sounds French as you pronounce it.
It should sound German.
Okay.
but I'm not going to bother either way.
Yeah, it doesn't affect the scientific content of your talk.
Here's a slightly out-of-date outline. Apparently I did send the update. I didn't update it before I sent it, but... So, perovskite is a material with the same crystal structure as calcium titanium oxide, which we can see a nice ball and stick model here, and it has a general chemical formula of ABX3, where A and B are cations and X is an anion.
Cubic? Are they cubic as you draw them, or it is a visual deception?
It's somewhat cubic.
So it depends.
It depends on exactly how you think about it.
Since this is a secondary presentation practice talk, so my question is why we need to talk about perovskite?
Mm-hmm.
I suppose I could move that up a little earlier in the talk. So perovskites are an emerging field in photovoltaics and LEDs, and they're used because they have easily tunable band gap, and they have good photoluminescence for LEDs, good word that I'm forgetting right now.
Is it good or better? If good, then is that what is the problem on existing technology, existing materials we used?
In photovoltaics, the potential is that they might improve further, and they're improving rapidly in photovoltaics. In LEDs, it's the tunability that's really what they're looking at, because you can tune it to emit throughout the entire visible spectrum, based on what your halide you use and how big the perovskite you make.
Are you going to show piano of Ramirez? If you were attending last year his talk, and the question that he was not able to answer from
The eye?
Huh?
The eye question?
No, not I. Piano.
Piano.
It was a question
I don't remember that.
of John Dr. Herberger. From the same paper, that in the title there is a word gamut, I don't know how to pronounce it, color gamut, and in addition to this range of beakers with luminescent perovskites, they show diagram where they change concentration and composition continuously and get any color, and by some reason the figure looks like piano if you look from the bottom, and this word discouraged Daniel to answer, like explain me why are you showing this piano.
I do not remember that question.
But you can show it until like this year we are ready to explain it.
This year Daniel might be ready to explain.
You should be. You as well. Okay, please. Sorry for interruption. Please continue.
Can I go to your title slide? What's the manual for layered books?
Not remember why I picked that.
Just informally.
So the idea was that it was based on the fact it was thin films we were looking at, but I don't remember why I specifically picked it.
Not because they're like onions, are they?
I hope not. Then this presentation is very long.
If you tell everything what is known to community and to yourself about perovskites, the answer will come at the end. But you may concentrate and try to give right now.
Oh, it's a good title.
Yeah,
At least,
title.
yeah. There's nothing wrong with it. It's just
Honestly, the part I liked the least about the title is the word materials, but Rogers went to prove it without that word.
No, layered is technical word. Is the main something. Yeah. So,
So
title
what-
is good. Title is okay. Yeah.
So what is bad about perovskites? What is their main weakness and challenge?
The environmental stability.
And for simple guys, what does it mean?
They decompose to moisture, to light, to heat, to oxygen.
And so they decompose when they interface
Yeah.
with stuff. So you need to seal them.
Okay.
And is there any advances to solve this problem if you do layered structure?
So the layered structure does have better stability.
Why?
The general idea is that the organic ligands that are involved act somewhat hydrophobic for the entire composition of the perovskite layer.
And also, what about the surface? Surface volume ratio.
So it would be it would have less surface area compared to zero-dimensional or quantum dot.
Well, maybe you sure if you have a bulk and
Yep.
you pour water, it starts
It
dissolving it.
dissolves.
Continues it until it dissolves everything.
Yeah.
And if you have layer structure, even if it is scratched, it will dissolve first layer and then it stops dissolving it because the hydrophobic ligands will prevent water from going further. So it's much more insulated, and it is one of the benefits. And you can say it right.
What is the improved photovoltaics? What does that means? You photovoltaic is just a device. What do you?
Let me tell a joke before you go further.
But before that, it's not. I'm not implying that your title is wrong or anything. I'm just saying. I'm just questioning it.
So the improved here is referencing compared to 3D perovskites, and it's almost entirely due to the improved stability.
So you're looking for stability on it.
Yeah.
There's you have a book of Shao Mukano on your desk.
Yeah.
So once he was presented on a conference and telling about his ancestors or whatever from place he is. So some of them were publishers in your little city and advertising once they were publishing Shakespeare and advertising what they did. It was like a bookstore with advertisement Romeo and Juliet, Shakespeare, second edition, improved. Improved for the text.
So you're just looking on stability only? How, I'm not sure how you do that computation.
So I am looking at more than just stability, but stability seems to be the main point that I'm between them. They seem to have fairly similar properties outside of stability between 3D and 2D. There's slight improvements or losses in either direction for that.
What makes it different from silicon in terms of like its use in the solar cell? What benefits are contrasting features?
It's a newer field, and the reason there's so much focus on it is it's had a very large growth in efficiency over the last 10 years or so since they started working with it. And the idea is it's, at least in theory, cheaper to make. It's not very easy to scale up to industrial sizes at the moment.
So I focus on the cheap part.
Yeah.
Because the thing, I guess, like for a lot of those people, silicon was like the novel
What is
technology back in the day. I guess, like for silicon, you have to heat it to insane temperatures to make solar cells out of them. Or like perovskites, you do everything in solution, lower temperature.
Yeah, it's cheaper, but there's
what is cheaper? The elementary components, ingredients, or the technology itself?
the elementary components.
Silicon itself.
Oh, I see what you're saying.
Elementary silicon is like
Yeah.
sand.
Yeah.
It's unlimited. The question is with technology. You need to.
Yeah.
So lead is a little more expensive than silicon, but processing is easier.
Yeah.
Perovskites.
Where- I think this is where we work. So as I mentioned earlier, apparently I need to reorganize my slides a little bit, apparently. But lead halide perovskites offer good, have a very tunable band gap. They have a relatively high or comparatively high stability. Enhanced photoluminescent quantum yields, long charge carrier lifetimes, which that was the one that was good for photovoltaics. And the charges are very mobile. And
Because you need to add few sentences
I
at
need-
least for each line. What is the main? What is the long charge carrier lifetime you mean? Want to know how it's help you to improve your photovoltaic?
so the long charge carrier lifetime, it allows the charges to separate. No, it's not right. So the enhanced charge mobilities are helpful for photovoltaics because they separate the charge, which is the goal for photovoltaics. You're trying to get the charge separated and make a circuit so you can gather the energy that you're trying to collect. Now remember why the long charge carrier lifetime matters.
But you still have time to until your
Yeah.
talk. So this is not yet quite research talk by its
Yeah.
regarding the department. So it's to some extent it is an exam, putting under question your knowledge,
Yeah.
right? And it's a chance to demonstrate your proficiency in something. So do not hesitate to tell some common knowledge here and there. So it doesn't need to, every word. You don't need to have all word, any word. Sorry. Combine new information from papers with trivial definitions. Either in the body of your talk or as backup slides.
Okay.
And when you mentioned relatively high stability and
Yeah.
also polynomials, you should have a reference point, right? Compared to what?
Oh, okay. Okay.
And also in secondary presentations, some people will look on the number of references you put on your slide. That means you studied more literature, you did more literature study.
Okay.
So far in these 3 slides, I've saw only one reference here.
Yeah.
So try to put more reference, it will give a good look on the slide.
Okay. And as we also discussed earlier, it has poor stability toward moisture. It tends to decompose, and it also decomposes at high temperature, which breaks it apart and prevents any effects that we're looking for from happening.
I guess just one quick comment. So can you give a good reason why I would have poor moisture stability? Or like an intuitive reason?
So in bulk, it's ionic. It's an ionic structure, and so it dissolves readily in water because of that.
Yeah.
So the blue and the black atoms here are cations, while the red ones here are anions, and it just forms an ionic solid.
So it's like a salt.
Yeah.
So it'll dissolve readily in anything cold.
Yep.
Yeah.
Yeah. Polar. I hope polar.
So that'd be a good reference point to mention, just like Dimitri said, just referencing things that people already know.
So then, as we look at the perovskites, well, we consider the different dimensions of. We consider them in different dimensions. You have your 3D, which is unrestricted in every dimension. The 2D is restricted in one dimension, which isn't the easiest to see in this model, but it's making a film. The 1D makes little rods and is restricted in 2 dimensions, where the 0D is restricted in all dimensions and it's just the perovskite cell surrounded by ligands.
In 1D, is this from the top view of this one?
From the way it looks to me is the rods are actually coming in and out of the board.
Okay.
That's the best picture I could find to try and illustrate 1D.
If you just look at the blue parts.
Yeah.
Just blue
Yeah, if you just look at the blue cell here, you can see that it sort of is forming a rod there. There's 4 or 5 in a row.
You can mention is an image of multiple rod. Yeah.
Yeah. So yeah, there's
This is not just one. Yeah.
12 rods in this image.
And one thing that might, oh, it always confused me for a while. So, I guess chemists they talk about like dimensionality different than like how you would like a nanostructure. So like when we talk about nanostructures, that's like 1D.
Yeah.
So it's like I always got confused looking at the literature. Like, when they describe 1D, like that phase, I would think nanowire. That doesn't necessarily imply that it's a nanowire
No. Yeah.
structure. So it's then like that might provoke a question from someone. So it's kind of
Considering the talk I had with Rogers about my title, it'd probably be from him. Because I had to explain what the 2D in the title meant. Because he was convinced that it shouldn't be 2D.
Oh, cool. It's ended. Interesting.
so I would emphasize that it's about the like how the crystal lattice is connected,
Okay,
rather than like the nanostructure.
sure, I can do that.
Please send this.
Get back.
No.
Okay.
And you're not limited in number of slides,
Yeah.
so you can
Yeah,
And-
I need to add more slides.
hand drawing or maybe borrow it from any review on confinement. Hand drawing is better because it will be only things that you like and you understand what is bulk, what is 2-dimensional, what is 0-dimensional. Before you go how this principle is implemented for perovskite, generally tell what is nanostructure.
Okay.
You even can make some models, like, or speak artistically. Like if sheets of
That's
ply-
probably the worst plan yet.
Sheets of plywood are 2-dimensional.
So, one type of 2-dimensional perovskite is the Ruddleson Popper phase perovskite, and it has a slightly different general formula compared to the regular perovskite. But what it is you have your regular perovskite layers, and separating these layers are rock salt like layers. So you end up with distinct perovskite, rock salt layers in your system.
And was this phase discovered or designed specifically for lead halide perovskites?
This phase was discovered in the 50s by I'm trying to remember the name. I'm trying to remember whether it was Ruddleson or Popperly that discovered it. I think it was Ruddleson that discovered it.
Natural. Is
It's one of the names. I don't remember which one. I have that paper on my computer though. It was discovered in 1957, and he was looking at an oxide peroxide.
So why are you suddenly talking about this type of phase? Is there any other thing, but
How are they connected?
how they are connected with the
Is
previous
like
slide?
you're presenting different dimensionality from
Yep.
0 to 3,
So-
and then you're telling those. What is it like 0 dimensional?
This is a type of two-dimensional perovskite.
You're writing it, but do we see it by human eye? How do you recognize that it is two-dimensional? It probably shows, but target undergraduate audience.
Okay.
Yeah, you're going to present a very general audience. Everyone can with your.
So if we,
So you assume that your audience understands what is periodic boundary conditions.
yeah, apparently that's probably my issue here. Is that's what I'm assuming.
Do not assume.
Yeah.
Define things like that.
So if we look at the model here, we see this rock salt-like layer here, and we have our perovskite layers, which are these diamond
So
shaped.
what is the importance of this one? What make this class of materials very special, and then that's why you are talking about these materials today.
So these materials are special because they are the precursor. That's not a good word.
Is this what you
What
modeled?
is the difference of A and B image?
The difference between A and B is the number of N here. So in B, we have two layers here, where in A we have one.
So
So
it's changed something, right? It's changed the distance between the two layers, right?
yeah. So it in B, N here equals 2, in A, N equals 1.
So you can tune the number of.
You can tune
N.
the number of N. And I need to come up with a good answer for your question. That's the question I need to have an answer for.
If you try to play logic, is it possible to create two-dimensional perovskites which will be not of the Rudelston-Popper phase?
Yeah.
But it will be another exotic phase.
Yeah.
So you are not bringing new stuff. You're just digging deeper into two dimensions, and you are claiming that if one tries to synthesize two-dimensional perovskites, they naturally, highly likely will be in this Rudelston-Popper phase.
One other question I have. Should I mention Dion Jacobson
Yes.
somewhere?
Yes.
Because I was looking at that and I have no idea where I should mention that, if I even should.
By now, it looks like it will be either Rudelston-Popper or this Dion
Yeah.
Jacobson. So if you represent plan of your talk as a flowchart, then you will have like multi-dimensional, then arrow for two-dimensional, and then another forking for Dion and Rudelston.
So the reason it's so important, and I need to come up with an answer for it on the last slide, but is in our inorganic organic hybrid perovskites, we have this large organic spacer that plays the role of the additional cation from the general Rudison hopper.
Mhm.
And what that organic spacer then acts like an insulator for the molecule, and it creates confinement wells, which I didn't put anywhere here yet. So the difference between the Dion Jacobson and the Rudison poplar, Ellen there, is this M here. In Dion Jacobson, it's equal to 1. In Rudison poplar, it's equal to 2.
Is it the only difference?
That's not the only difference.
But can you speak from the point of view of right now? You are speaking. I'm not criticizing, just observing. You're speaking like a mathematician.
Okay.
So formal properties. But if you speak as a synthetic chemist, you show a table, and majority of your audience will be chemical chemists. So if you look, yes, number 1 and number 2 ligands, what is their difference?
The difference is one is a diammonium, one is just a regular ammonium ligand.
Okay.
So in the case of number 1, the ammonium is what binds to the perovskite layer, and you end up with a tail coming off to the middle. So you need another second one down here. Where in the diammonium case, you end up with an ammonium on both sides. So it can directly bond to both perovskite layers.
Excellent, excellent. And
So
go ahead.
which causes in the Rudison popper instance for your 2 perovskite layers to be offset. So these ones are actually drawn as Dion Jacobson, where they're in line.
Okay. I have a quick question. Mechanism of binding. Like, there is no doubt that you understand it, but it's better to verbalize it, speak it slowly. Like, why ammonium group binds to the surface? What does it do to the surface?
In these models, these red atoms here are going to be halides, so they're an anion, and they ionically bond to the cation that is ammonium.
Yes. Is there a smart word from basic chemistry? Like bringing system to a neutral, compensating charges, something like this. Establishing stoichiometric balance of anions and cations.
Establishing a neutral charge on the molecule?
Okay. And it's electrostatic attraction.
Yes, it's an electrostatic attraction.
So any system which is not neutral will practice electrostatic attraction substantially.
Yes.
And so now you're explaining this Rudolph Popper and Dion Jacobson from synthetic point of view. Depending on which ligands you have purchased, you will automatically synthesize either one or another type of perovskite.
I assume you will get a lot of questions from these slides. There are a lot of chemicals molecule here.
Yep.
What is the purpose of this series of molecules? Why are you showing us that?
So these are some of the possible molecules that can act as the organic spacer in the hybrid perovskite.
So what is the main feature of this molecule, the design only this molecule?
So the main feature is you're going to have an ammonium, or in a few cases phosphate. And then you're going to have either a large aliphatic or aromatic. Aliphatic or, it's not aromatic, it's another word that's,
What is that?
I have to look that word up again, but
31 and 32 are aromatic.
it's the one that means you have a big ring on the end. So it creates a space between the perovskite layers. And
So you have a two purpose. One is spacing, another one is connector. How is connecting to the
Yeah.
two layers, and what's the spacing between these two layers?
Yeah. So yeah, there's a purpose for spacing and a purpose for connecting the two perovskite layers.
And little question, not scientific. If I am sitting in the audience with selfish purposes, if I want to apply for a job as a postdoc in this group, how do I know where it is and who is the person who to whom I should apply? Typically, first author is not the group leader.
My references are very disorganized right now. I need to redo all of them anyway. I can change to the group leader if that would be better.
Or you can just verbally tell, either show portrait or say from which university it is.
Okay.
Is it like one any random second tier university or one of the like first three?
Yeah.
You don't remember? It's pretty close
I
to
don't
us.
remember this one. I think
it's
was this Northwestern?
Yes, in Chicago. So you probably can invite. And the name of the PI is very exotic Greek. So he's Mercurius, and last name Canadius.
Okay. Yeah, I need to redo all the references anyway because I have like 5 different styles.
So one question you might get comparing your 1 and 2 ligand.
1 and 2.
So for the diammonium, they're going to be attracted by charge. But for your second ligand, but for your first ligand, it only has one charge group on it. So then how does the other side stabilize? Or is it like capping at the very end of the chain, wherever it terminates? Does that make sense? Or like if they're layered on top of each other, there's eventually going to be a layer like at the very top.
Okay.
So does it go there, or can you actually put it on any of the layers?
So it acts in a van der Waals interactions. They interact much like long chain hydrocarbons form bilayers.
So you can put them anywhere.
Yeah.
In the layer.
So yeah, you're going to have one coming down and another one coming up, and it's going to keep doing that and form a layer.
So I'm just wondering, it's not about your slide, just wondering that when you connect these two layers, is it 2 nanoplates or is it make it just one single nanoplates? Is each layer an interactive layer? Which one should I consider as a 1 nanoplate? Both? Just 1 nanoplates connected by this spacer? Or in your image, is there 2 nanoplates? I'm just trying to understand that because I don't know much about perovskite.
I understand his question. I'm really.
I don't know how I
I'm not
understand
sure I
these
understand the
questions.
question.
There is a confusion. Images and explanation were not digested sufficiently to Jabal is not ready to draw model of this rather than perovskite himself.
Okay.
Give him more guidance.
Suppose like in your image, first one,
Yeah.
is there 2 nanoplates or 1 nanoplates?
So you imply that we all, well, we yes, but generally everyone in your audience is comfortable with concept of periodic boundary conditions. Good. Now, how should we apply this concept to these images? Because you didn't pedal this PBC periodic boundary conditions, it may look
Yeah, that's
just
why I didn't say that
it is
before.
just a single two-dimensional layer and nothing else in a vacuum.
Oh. So this is going to be periodic in the, I would want to call it the Z direction, but you might want to call
So
it the
this
Y
is
direction.
one of your periodic cell.
So it's
Yeah, it's a periodic.
Okay.
So it's infinite stack
Yeah.
of sheets. So it's basically as a plywood.
Oh,
So you're going to have more organic layers coming off here and then another perovskite.
And you probably can do explanation on the kindergarten level, or even bring bucket with a glue and a couple of paper sheets. Like, so here is the perovskite, here is the organic layer, another perovskite, another, and just stack
Yeah,
it up.
So that's why he's saying layered materials.
Yes, yes.
Layer to nanoparticle.
Uh-huh. So it's an infinite stack. Or
It's not just individual nanoplates. It's a
no,
layer.
no, individuals they are not good. They will be not stable and they will corrugate and buckle easily.
Yeah.
And here the same as in plywood.
Yeah.
Each individual sheet is very flexible and together it's better than regular wood.
Yeah, but
So yeah,
what
to actually make a proper periodic cell, you would need another set of these blue lines as well, because they only show they actually only show it in this one. They don't even show it in the bigger ones in their figure for some reason. Their figure actually goes up to n equals 4.
now you got why he's saying layer. Oh, sorry about that. It's layered. Yeah.
It's good.
So you can make like a cheesy PowerPoint slide, just like a big rectangle, and just make like slices.
Okay. That's just,
And make some animation yourself. No, you don't need to put everything from. Animation means not very high quality image, just helping image, which will help us to understand.
Maybe
what
like
is
Okay.
sheets are flying in and laying on top of each other, or whatever is comfortable for you. And another question
Yep.
on the same aspect. How well the atomic structure of this two-dimensional perovskites is known? Is there ambiguity, or it is 100% known for community? Are there limitations for determination of their interatomic distances and positions of ions? Assuming
No.
that Dr. Ugrinov, Angel, can sit in the audience.
the small perovskite layers are well known. And so the ones with small number of perovskite layers are well known. But the larger ones are expected to be.
With some more uncertainty. But what is the standard way to find atomic structure from experiment?
X-ray crystallography.
Yeah. Is it applicable to these two-dimensional perovskites?
Yeah.
I bet yes. You may refer to it and impress everyone by breadth of your knowledge.
I was purposely ignoring those figures, but okay.
I have a question. So for the organic spacer group,
Yep.
you have some very small molecules, and you have also some bulky molecules.
Yep.
Is there any kind of effects?
So there is some evidence that what spacer group you use affects stability. And there is also, not so much in the Ruddleston Popper, but in the D.N. Jacobson, some in the smaller ones you can get some interaction between the different quantum wells of the perovskite layers with the smaller organic spacers.
For a solar cell, would you want water distance between layers or small distance?
A lot of distance.
Would make
What is
sense.
expected for you? So you said longer distance?
Yeah,
Why?
because that would separate the wells further and allow them to the perovskites to interact greater with the incoming light. Or it's not the right word, but
I don't know the answer either, but I would imagine like
So
You would get better efficiency if it just stayed on one layer instead of
So is-
hopping back and forth between layers.
I think didn't add that yet. It's 9.
So is this all molecules taken from that paper?
What?
Is this all molecule is taken from this paper, reference paper?
So yeah, this is all from the same reference.
So what is their conclusions on this molecule?
What is this? What?
Their conclusions?
That they can make them probably.
Pretty much.
So they just synthesize it, or they just make
This-
some
this-
comment on?
This
What is
was
this one
commented
better?
on what could be done. And this is actually a review paper.
That's good. Then yeah, you will get all information in one paper.
I include that. No, I didn't. Apparently, I hadn't, when I emailed this, I hadn't added the schematic of the wells yet. Get that back there. I'm attempting to draw.
So, does it work?
There we go. So you end up with this type of structure for the band. So you have your organic layers and your perovskite layers like this.
So I don't get it. Can you tell me a little bit more? Which one is organic layer you say?
So the organic layer are going to be the high. This backwards. Might be doing this backwards.
So where is perovskite and where is the organic layer? It's really helpful. Figure.
That's a terrible drawing, but
Should it be opposite?
yes, it should be.
So the perovskite smaller gap,
Yeah, the perovskite has a small gap.
yeah, and white gap is organic layer. Yeah, it's great.
I like how I drew that.
Hmm?
Wish I had added that from the paper. There's actually makes sense to me. So, one of the reasons that they wanted that perovskites became such a interesting thing to look at was the tunability of the band gap. So as you see here, you can make solutions that emit in the entire visible spectrum. And you do that by changing the halide and going down the periodic table, as well as changing the size of the molecule or the perovskite itself. And these are all 0D perovskite, so they probably should be earlier anyway.
But the same principle of quantum confinement will work.
But yeah, the same principle works with the 2D. It's yeah. And you can see that it also allows you to adjust the absorbance of the material, which is helpful for photovoltaics. It allows you to absorb more of the light spectrum, or if you have some specific reason, you absorb a specific part of the light spectrum.
So in general, which halide content would be like the most optimal for a solar cell?
In general, the iodine bromide mix.
Yeah, because there's some theory that
It's
around 700
Yeah.
nanometers, like the optimal.
gives you the best, and it's also appears to be one of the more stable ones.
What's the size of these quantum dots?
I do not remember. I know they used a range of sizes to make the different colors.
But from the top of the head, are they more like 1 nanometer or more like micrometer, or 100 nanometers or 10 nanometers? Just roughly which range?
Tens of nanometers. Irritating. And if you look, and the camera screen is covering up the part that's interesting, but you can see here the perovskite photocell efficiencies, and it actually starts somewhere in this range, and it has increased very quickly, getting up to now around 25% efficient. When this, which you can see,
So it's not that terminal number is champion among all samples, but it's impressive growth.
It has a very impressive growth, and they do have a newer figure of this that I need to update it with, that it's starting to slow down a bit, but it's still increasing faster than basically anything else on the graph.
Mm-hmm.
So the use of perovskites in photovoltaics has a long carrier lifetime. Tunable band gap, a bunch of stuff that I've already talked about. This is earlier.
So in terms of things we compute,
Things
like
we
rates,
compute.
how is the carrier lifetime really? I guess, is this like a literature review, or is it also research?
It's primarily a literature review. They let us choose something that can be useful for our research.
Oh, so you're not presenting on anything you've
Yeah.
calculated yet? Okay.
It's more like exam of ability to review and summarize literature.
Okay.
So yeah, it's meant to be a pure lit review.
So I was gonna say, if you're gonna present some of your dynamics results, you might want to relate carrier lifetime to the non-radiative lifetimes. I guess since you're not doing that, it wouldn't make as much sense.
At the time when the regulations for this exam were designed, maybe several decades ago, it was assumed that at the beginning of second year, a researcher is not capable to generate any new data. study a lot before doing actual research. Which is changing now, but
So the major issue with the use of perovskites in photovoltaics is its stability. It is sensitive to many different environmental stimuli, and due to that they're having issues scaling it up from lab scale to industrial scale.
so what's a typical time for degrading of a sample?
Typical time in they've increased it to about a year right now, but it's not uncommon for half a year, especially in.
For two-dimensional perovskites or regular?
So for two-dimensional, it's about a year,
And for regular, just for comparison?
3 to 6 months.
It's very optimistic.
It depends on how well they manage to protect it from water.
And if you do not protect it,
If you do not protect it from water, a few hours,
Yeah.
a day.
Yeah, yeah. So you may pronounce this data to tell how important it is. And after, if it degrades, how does it change its properties? What does it mean degrades in respect to ability to emit light or collect light?
It degrades to being virtually worthless as emitting light. I don't honestly know what's absorbing.
But what's a mechanism? Like perovskites absorb and emit depending on this confinement in infrared or visible, something like red color.
Yeah.
What happens if you pour water on this sample and make it to absorb or emit?
It would be colorless.
Yes, so their gap, it will decompose to precursors,
Yep.
and their gaps are
Which have
in UV.
right? Yeah.
So they may absorb or emit, but it will be in UV and it will be not useful for technology.
And the precursors are fairly toxic to the environment as well, at least in the lead halide perovskite cases that I'm looking at right here.
Do you have photographs, images of the perovskite samples? Not the emitting, but regular that used for photovoltaics for absorbing.
Like just a picture of what it looks like,
Yes.
like the solar cell. I don't think I added one, but I definitely could. I need something to fill all this white space on this
and
one.
you may find, and it's everyone right now.
I did see some pictures of it. I just didn't add
So
any.
it looks blackish,
Yeah.
and after degrading with water, it becomes like yellowish or transparent, as you've talked.
Yeah, I need something to fill this white space. I just hadn't figured out what. And I did see pictures of that use. So in a photovoltaic cell, and I want to completely redo this slide. I just put this up so I had it here. The way it works is you have your active layer, which in our case is the perovskite, and then you have an electron transport and a hole transport layer, which allow the electrons and holes to move through the material. And you have your transparent side, which is usually ITO, which an hour ago I could have told you what that was.
So O probably stands for oxide.
It's something titanium oxide. I don't remember what the
O
I
stands for oxide.
I don't
But
remember what the I is.
T may not stand for titanium. Where do people store food preserves? In which metal?
Tin?
Mm-hmm. So it's primarily tin oxide.
Okay.
And then it is doped either by indium for I or by fluorine.
For F.
So what is this FTO and ITO, how do they appear visually? You already told it. I'm
They're
just returning back.
Transparent.
Yes, so it's transparent metals.
So the light will come in through here, and it'll excite an electron from the perovskite up to somewhere in the valence band, and the electron will move through the electron transport layer, while the hole will move through the hole transport layer and will make a circuit, which is what I need to actually put in here, but so I'll just keep moving around and eventually make a full circuit.
What are the typical electron transport layer and also hole transport layer?
It was PDAC, PSS. I don't know.
Oh, okay. So it's
I'm trying to remember.
conjugated polymers.
Yeah, it was a conjugated polymer, and
Okay, but it's an option.
that's one of the options. Yeah.
Okay. What else? Probably buckyballs.
Buckyballs. Okay.
What else?
Are there any inorganic materials?
There is, and I'm trying to
You were mentioning one of the
think of what
materials,
it is.
and you were offering to use it as a transparent anode based on the abbreviation of letter T,
Tin oxide
titanium oxide.
or titanium oxide.
So tin oxide transparent and titanium.
That's where the titanium was.
Yes.
Okay.
Is there any interaction between electron transport layer and perovskite?
There should be an interface layer where it allows the electron to, the charge to transfer.
So you already did a little interview with Dr. Rogers, right?
Sort of. It was very informal, very quick, but yeah.
It's good. It's good. Prepare for a good way to prepare for presentation. You may want to make a similar quick informal interview with Dr. Rasmussen, because if he will be in the audience during presentation of this one, he will ask questions because it's his how to say specialization.
Okay.
And during your talk, it will be his turn to ask you questions. Before talk, it's your turn to ask him questions.
So, that's something I need to explain earlier. Okay. So one of the issues with this is its thermal stability. And as you can see in this graph, the red boxes are heating steps where the blue are cooling steps. So the photoluminescence decreases with each heating step and gets worse. And then they also have cooling steps to show its bounce back. So there are a couple ways that they can try and fix this. The first way is substituting different chemicals actually into the perovskite, or doping the perovskite in different ways. Specifically, and I didn't mention this when this is something I do need to mention earlier. But in so that's wide. So in your perovskite, the blue atoms here are a monovalent cation. That is often represented, or that is often, methyl ammonium is often used for that location. So one of the suggestions to improve the thermal stability is to substitute either the cesium ion or the formamidium? Is that how you pronounce that?
Do you know, can you draw a chemical structure?
Yeah.
So you gave up drawing on the screen. That's fine.
Actually, there should be a plus there as well, but
1 plus or 2 pluses?
1. So formamidium.
Mm-hmm.
Okay.
So we come across the term Goldschmidt tolerance. You're reading, so you're talking about like stability of a perovskite. That's something that you'd want to mention.
Okay.
'Cause that's essentially what they're testing.
Okay.
And this is because with temperature, you're essentially changing like the crystal phase
Yep.
and its ability to bounce back and forth. And then that has to do with those cations that you mentioned. Some are too small,
Yeah.
and so that leads to the degradation of phase change.
Okay.
Because that might provoke a question like, why does heating change the sample so much?
Okay.
And what does
And-
PL have to do with it if you're talking about photovoltaics?
Yeah, I want to look through better and find better slides for this, but those were the only figures outside of some really not good looking supplemental figures that I could find.
I think this is a good way to describe it. You just want to give the audience a little more background as
Okay.
to how this is showing this
Sure.
stability of the perovskite.
The other suggestion for dealing with the thermal stability issue is using an inorganic encapsulation method, which is what this graph is showing. So we have cesium lead bromide perovskite, and they used a
Okay, later on you
I need
add
to look that up.
dictionary.
I need, yeah. And you see that it does have a significantly slower rate of falling intensity compared to the unencapsulated perovskite. And if I remember, it goes to 100 hours at the end, yeah. As you can't read the figure that far.
This still for two-dimensional perovskite?
These ones were, if I remember correctly, 3D for this and 0D for this.
So you're showing what generally.
Yeah, this is general. I I couldn't find any 2D specific for this one. Yeah. And this one, it compares the 2D with the 3D, so the red lines are 2D and the blue lines are 3D. And it's also, it's looking at both light, which is the two on the left, where the two on the right are looking at humidity. So we see in all cases that 3D drops off quicker than the 2D. And we see that if you encapsulate, and these ones are encapsulated with polymers, that the 2D doesn't fall off as bad as it did in the unencapsulated state.
Is there any explanation like that?
So the encapsulated is because the water doesn't get access to it. There is some effect from residual water. As for the reason that the 3D goes faster, it's because it, as we discussed earlier, is going to dissolve in water. And it also is going to decompose faster under light for the same reason, or the same reasoning. So here we're just looking at Ruddleston Poplar stability versus the 3D. And if you look at our graph, we do see that once again the red is 2D and the black is 3D.
And what is PCE?
What? PCE.
What is on the y-axis? So if it is a photovoltaic, what is the main outcome of the photovoltaic cell?
Energy.
Well, energy is too general, but practically, what comes out of bias?
Efficiency.
No, it's more from the point of end user, but as an engineer. From photodiode.
Current.
Yes. So letter C is probably for the current. Current comes under which condition? If this photovoltaic cell is irradiated by photons. Okay. And E?
Efficiency.
Okay, so for the current efficiency. Likely. I can be wrong, but it looks this way.
And so as we see, and this one goes up to 1600 hours. We see that the 2D Ruddleston Poplar model efficiency decreases slower than the 3D model.
And what is PTA?
Phenyl triammonium.
Enough for me.
Phenyl trimethylammonium. That's what the key is. That's the organic spacer they used for this specific model. And this group found that there was a significant effect to the thickness of the film on the stability. And there was a moderate effect of the choice of organic ligand to the stability.
So when you're saying stability, it may make it confused in the or a second representation because it will be general audience.
Okay.
So is it a structural stability or is something?
Stability from decomposition. Does that make more sense?
How you relate with decomposition with this figure?
Okay. So the Ruddleston poplar shows a smaller decrease in efficiency than the 3D, indicating that its structure has decomposed less than the 3D structure has.
Do you want to correct anything in the equation before you start presenting?
There's a bunch of subscripts that are missing.
Can you add them by hand?
And I noticed that after I emailed it to you, and I started fixing them on my more updated copy.
Super. That's great.
And there's also several subscripts that aren't actually subscripts as well. So what this does is the Ruddleston poplar model does is it creates quantum wells in our material, and they act like or similar to particle in a box for the model. And
Can I add something right away?
So gap of the material is whatever it was in bulk plus correction due to confinement. And then correction to the confinement will be proportional to the equation that you're presenting.
okay,
So if all L capitals are equal to infinity, then this delta E will be equal 0. And it will be the same as in the bulk.
in this situation, only 2 of them are equal to infinity because we're looking at a 2D.
What is M here?
M is mass, and that's another thing I don't know why there's a star there.
It's just mass.
Mass of what?
It's mass of the electron.
Yes. And mass of electron in solid state is different than in vacuum.
Yeah.
Why?
I have no idea why.
Is that due to special relativity by any chance? Or nothing?
Well, you're right that due to special relativity, mass
changes when things are moving quickly, but here is a different effect.
Okay.
Because it interacts with lattice and it's getting stopped, there is a friction, and in average it will be same as if mass of the electron will be lighter or heavier.
It's like a viscosity.
Okay.
You can think of it.
Yeah, I know it's changes, but yeah,
And it changes substantially, so it can change like 10 times
Yeah.
bigger or smaller,
okay.
depending on the material. The next question that I do not know answer. What would be the effective mass of electron in perovskites?
Pretty big.
Bigger than one in like.
Yeah, I think it's like 0.1. So it moves. So it moves pretty slowly.
So it's less than.
Yeah, it's
It
less. It's less than the free mass. So it interacts with the lattice a lot.
Okay.
Did you want to illustrate this equation with any figures?
Sure. So I'm going to do a 1D figure because I don't know how I could draw more than that.
Mm-hmm.
So you have this type of very good job drawing that one. Or that one, but
So what can we suggest David to correct in this figure to help the goal of his presentation?
For
Group similar terms.
No.
put arrow to
Huh?
the energy bar, you need to be arrow to indicate is very infinite barrier.
Yes. I'm impatient to. So.
better at drawing straight lines than I am.
I was practicing. So there is.
So the 0 point energy.
Yes,
Okay.
exactly. So you can show it.
Okay.
Due to quantum confinement, the energy will be larger than zero, and it is main effect.
Okay.
Good. I think it will convince majority of the audience.
Sure. I can add that.
Uh-huh.
So as we increase the perovskite layer size, we increase the size of our box, and because of that, it redshifts all the absorption and emission.
Or if one thinks in the opposite way, if the length of the layer is infinite, it is the fundamental gap, and
Yeah.
as soon as you go opposite direction, making it thinner and thinner, it blue shifts.
Blue shifts. If you go from 3D and start confining it, it'll blue shift it. So if we look at it, and I need to make this bigger, this first bar here, this red color is our 3D.
And top is absorption.
Top is absorption, bottom is photoluminescence.
Mhm.
And as we go smaller and smaller perovskite layer size, from 7 down to 1, it blue shifts more and more, eventually getting down to 2.2 EV, which is almost into the UV range.
Do not tell this. 2.2 electron volts. Which color is it?
Is it red?
Huh?
Red.
2.2 is violet. 2.2 is violet.
Violet?
Yeah.
I will double check. How many nanometers? So it's like 600? Is it valid?
2.2 is a 563 nanometer.
Okay, 560. And what is the border of the visible and UV?
700. 7 is 450 to 700.
450. So it's 100 nanometers more,
Okay,
or even 200. So it's still visible.
sure.
The yellow color line.
It's still yellow. I thought so. We don't care, but
I'm
some
thinking things through.
some people in the audience will be professional spectroscopists, and they will be not happy if you mix purple with yellow. So purple will be something like 3,
Yeah.
right?
Yeah, something like that.
Purple is like
2.8.
2.8.
Or 3Vs, 4 to 13.
300 maybe. Yeah.
But it's like public
About 440.
information,
Yeah.
color given Wikipedia. Just check it so that you do not say with confidence things that you're not sure about.
Okay.
So this figure, this is all computational work on experimental experiments. How
This
did you
one,
get, how did you get the absorption and emission?
Seems like experimental.
this was experimental, if I remember.
Yeah, figures look like experimental.
For it's clear that for 7 layers, computation is not possible today.
Take forever.
And your talk doesn't have any papers on computations.
I did not add any yet.
Yeah, I have some comments. There's a guy named Filippo, who, like, half of his, like, everything he publishes is about defects. Or seems that way anyway. So he has a lot of,
Yeah, I need to.
yeah, so
I
he
need
was,
to expand the quantum confinement section. I need to expand the stability section. I need to reorganize the intro, and I figured I would have to add something yet to get me up to the time,
Yeah.
which I figured was going to be something computational.
Majority of the audience who will be giving you grades are not computational. So it's fine to have experiment, the presentation 80% experimental, but just mention that if there will be no experiment, it will mean that you will be the first in the world. It would be great.
Mhm.
But if it is not, you can just mention there are some works and they either accomplish something or at least identify challenges
Okay.
that only you can solve.
At sign.
And now you're telling, hey guys, you all can read. Just enjoy what is typed.
I find it weird that I have an at sign there.
Is it typos?
Yeah, the at sign should be 2. So the perovskites are emerging material that has shown great improvements in photovoltaics. It has some issues to be resolved to determine, has some issues that need to be resolved before it can be used industrially or industrially. I don't know if there's a better word than that.
You can say commercial even.
Yeah, I was thinking commercially, but I think industrially might be the better word there. Or maybe both. Either way, the major issue currently preventing its use is its stability issues. But it does seem that using the 2D perovskites improved the stability of of the cell compared to the 3D perovskites. And we see that we can easily tune the band gap by changing the size and the composition of the perovskite. I sighed that I apparently just have a title on at this point.
So in your conclusion, you said the 2D is more stable than in 3D. So what is the more abundant in nature, actually? 2D or 3D materials?
So,
And what do you mean nature?
Perovskite materials.
Because it's
so the 3D are the more common material at the moment,
Where you say the less stable than 2D.
but they are less stable, but neither of these are naturally found. They're all
what
made.
do you mean nature?
But perovskite is available in
What do you
nature.
perovskite of what?
So,
Okay, so that means there is some other question here.
So it's
so that
So I don't
so naturally most perovskites are oxides, which I was focusing on halide perovskites.
Oh, okay.
and oxides are stable.
Oxides are more stable.
So your conclusion page to me is very, very in general. So I'm just wondering, is this all 3-4 conclusions can be made without your whole presentation, isn't it? Suppose like fourth one, changing the size of the perovskite layer allow the greater band gap tunability is very general, isn't it?
Yeah.
So most of the papers that you are showing are very recent. They are this year, 19, and the year is not yet finished. It means that it is really emergent area. But are they all just mumbling, or there are really discoveries? Like which part of this statement are discoveries made in the papers that you have read, and which are just common sense expectations?
So the first and the fourth are the common sense expectations. The second, and by extension the third, were expected, but it's more recent that they've been putting effort into proving or determining.
So I guess you can be more specific based on your presentation because you have shown a lot of results and important
Okay.
things. Yeah.
Okay.
So one thing that you glossed over, what you've presented previously, is like how to incorporate these into solar cells.
Okay.
Because they could either go two ways. They could, if this is your electron and hole transport layer,
Okay.
they could stack.
So you're
So-
saying
It's like how are they arranged within the cell?
you're saying I should actually make something that explains how it's shown in like. So make something like this except with the perovskite to show how it's orientated in there.
Mm-hmm. London was discussing, right? Recently.
Like you didn't mention it. Like people might not notice, but like they have to be oriented one way
Yes.
specifically for it to work in the cell.
Oh yeah, have fun.
Okay. You disappear.
I'm just walking out of your way.
Okay, thank you.
So how many paper you have reviewed for this presentation? I mean, not exactly. I mean,
I think there were 8 in it at the moment, but I'd have to go through and check.
Yeah, I guess you need a little bit more.
Yeah, I do need more, and I have a few for quantum confinement that I didn't put in it yet, and I need to find some more for stability, for the stability sections, and I'm almost certainly going to need another section, which is probably going to be something computational.
you may want to do is to show that if you arrange two-dimensional layers in this way, then it will be insulating.
Yep.
So one needs to put them as a books on a bookshelf, right?
Yeah,
The direction of charge mobility.
because they're
Yeah, which direction is charge mobilized? So in spacer molecule slide, you have shown us a number of molecules and you have a discussion about the spacer and also orientation of a layer.
so.
Yeah, this-
So this layer right here is an insulator.
Yeah.
So if we have our electron transport and our whole transport layer here, it's going to insulate.
But you have no other discussion based on these things, how it will change the overall photovoltaic devices efficiency. You have shown us different way of spacing and everything, but you didn't show any result of that different outcomes.
Okay.
And it might be that since it's like so early still, there might not be a lot of studies like on the effect of different spacers for solar cells. There's probably a couple over there.
I guess you can add one or two slides, follow up of this slide and this one.
Now I have a question.
Yep.
I guess this work is primarily focused on experiment work, right?
Yeah.
So I'm just wondering, how did you actually synthesize this kind of a structure? Experiment.
So they primarily used a hot casting method, which I really need to look up more of how it actually works. They somehow inject the primary materials when it's hot and it makes them, but I don't understand how it works entirely. So
So in your colorful stoichiometric equation, you have A prime, A, B, and X.
Yep.
And you have fractions, proportions,
Mhm.
m and minus 1, n, 3, and plus 1. Is it something that comes out after synthesis, or when you fabricate your material, you set up these proportions?
So you want to set up these proportions when you do it.
Right.
Otherwise, you're going to get very random, and there's actually starting to be some evidence that they aren't completely homogeneous layers anyway.
Exactly. And by fine-tuning of these proportions, you intentionally facilitate growth of a certain thickness,
Yeah.
because they're different by these proportions. So you just, whatever is experimental techniques, maybe syringes, you measure how many precursors and you inject them simultaneously.
I think I saw one paper recently. It's like they could get them to self-assemble, so they made platelets, and they're terminated with ligands, and then they either evaporate them slowly or something, and they just kind of layer stuff each other.
They do. And the question is how to facilitate certain thickness of layer. Is it like monoatomic thickness layer, or it is several?
Yeah, I guess, and that would be depend on how they made the platelets, which would, yeah, it gets back to the original question.
Because if it is just experiment work, then if you do not talk about synthesis, it's a little bit weird.
Okay.
And online, a lot of people were bragging how they synthesize.
Oh, yeah.
And it's not a problem to include video.
Well, a few of the ones from these papers were bragging about it in their paper.
I have a question.
Yep.
Actually, two. Well, maybe more. So, in fact, you are doing theory. Right? computation.
Assume.
Yes. And there could be, you may plan to have a little mention of the computation and theory in your slides. So, two questions. Which challenges to experiment and engineering can be resolved by computation? Like, is computation needed, or everything is done just by attempts and trials, and computation is only our entertainment? Do you see any challenges, or maybe in the papers these experimental groups pose unresolved questions that they would need help from computation to resolve?
The
I guess Ewan asked you a question about it. Really, you didn't follow up in depth. But like, if you go to your photovoltaic cell slide, so you have your perovskite layer, and then the 2 layers above and below it.
yeah.
It's like, how does, like, you create an interface layer,
Yeah.
and how does the interface affect your performance of the cell?
So we can look at how the interfaces in the photovoltaic cell. We can examine other spacer molecules that may be more difficult or more expensive to synthesize and see if they're even worth attempting experimentally. Probably not the best way to word that.
We're on the right track, though. Like, you've probably seen Landon's presentations
Yeah.
a couple of times. It's like comparing whether there's functional groups at the surface compared to whether there's not. So it's just like the microscopic details and how those could affect performance.
General answer. I'm not sure if it is correct, but if experimental audience gives a hard time to a computational presenter, the general answer is that computation helps to save chemicals. So one can compute stuff that hasn't been synthesized yet and predict whether it will be more or less efficient. So if you have theory-guided synthesis.
Okay.
So it's just to answer in general, which maybe sometimes synthesis is much cheaper than computation. But question number 2. Suppose we answered the first one. Computation can help in a positive way to experiment.
Okay.
But what are the challenges of computation to itself? Like, are there specific challenges to compute two-dimensional layered perovskites that are, what is different in them compared to other systems that are being computed, like small molecules or bulk? Why they are not easy to compute?
Well, for starters, they're relatively large systems, so it takes a lot more computing power to do them to begin with. In addition, they have some large, or heavy metals,
Which will maybe contribute spin orbit.
which will contribute to spin orbit coupling or heavy metals. Is there a better way to say heavy metals there?
Mhm. Well,
Or does that work?
what about excitons? Like if the electron and hole attract each other electrostatically in a slight way, not very strong energy.
Okay.
And if you have free electron and free hole in three-dimensional bulk, they have a lot of ways to avoid each other.
Yeah.
If you are in zero-dimensional quantum dot, they do not have ways to avoid each other. They are just jammed together in a little compartment.
Okay.
What is in two-dimensional?
In 2 dimension, it's relatively free yet.
But there are less ways for...
There are less ways compared to 3D.
Yes, and excitonic effects will give larger correction to optical transition energy.
Okay.
So there are computational works telling that anything we would do with ground state DFT, we will have noticeable error because it will miss, for this specific system, it will miss optical attraction. So for two-dimensional, it needs to be taken into account.
Okay.
It is a challenge for weak systems.
Mm-hmm.
More questions? Well, if no, let's thank David. And please collect our writings, unless authors of writings will reject to give it to you.
And just counting them up quick to bet, there's 12 references in this.
Oh, that's cool. How many references do you want to put in your doctoral thesis?
I'm okay with one, but I doubt anyone else would be.
But in order to avoid problems.
I have no idea.
But roughly, what's your estimate?
Several hundred.
1 a page, 2 a page maybe.
So, well, like 200 will be sufficient. You don't need more. Other volunteers for Tuesday to present by review? If no, we will discuss it privately if it needs to be on Tuesday. Well, many thanks for helping David. Meeting is dismissed. Thanks for coming, and I'll stay here to chat a bit one-to-one.